We're going to pick right back up where we left off in the last video. We're still looking at graphs of the sine and cosine functions, and now what we're going to do is we're going to look to see how a transformation will affect the graph by multiplying the trig function by some constant that's not equal to 0 or not equal to 1. Of course, if it was equal to 0, it would just take out the whole function, and if it was equal to 1, it wouldn't change it. So what we're going to do is we're going to multiply that function by some constant, which we're going to call a, and we're going to see how it dilates, how it stretches or shrinks the graph as you multiply by a. If the absolute value of a, remember if a is negative, we're going to have reflection, but if the absolute value of a is greater than 1, then we have a vertical stretch. We know this from before. We've done these types of graphs with polynomials. Now we're going to do them with trig functions. And if the absolute value of a is between 0 and 1, we have a vertical shrinking or compressing by that factor of the absolute value of a. Now I left the two graphs up that I had from the previous video, and what I'm going to do is I'm going to do a transformation by multiplying these trig functions of sine and cosine by constants. And instead of starting with this one, we're going to come over to here. We're going to start with this one we had before, and this is graph y equals the cosine of x. So now, which of course the domain is all reals and the range is between -1 and 1 inclusive. Now what we're going to do is we're going to multiply that cosine of x function by 2, outside here by 2, and we're going to see how that affects the graph. Now according to this, the absolute value of 2 of course is greater than 1, it should be some type of a vertical stretch. Now, as you can see here, when I graphed this the first time, I had a very lengthy chart, if you remember from the last video, with all these values. You can see all the little green dots there on the pink. But now I'm only going to graph key values to get an idea of what's going on. Because if the cosine of x is 0, you see here at the x-intercepts, the cosine of x is 0, the y value is 0. Well, when you multiply 2 times something that equals 0, you're going to get 0. That is not going to change my x-intercepts. My x-intercepts are going to be the same. So what I'm going to do is I'm going to kind of look for my highs and lows, and I'm going to kind of do my very best to make it look like a sine wave or a cosine wave. So now, what are we going to do? We're going to just plug in these 5 values here. If I plug in 0, the cosine of 0 is 1 times 2 is 2. If I plug in pi over 2, the cosine of pi over 2 is 0 times 2 is 0. If I plug in pi, the cosine of pi is -1 times 2 is -2. If I plug in 3 pi over 2, the cosine of that is 0 times 2 is 0. And if I plug in 2 pi, which is coterminal with 0 there, the cosine of 2 pi is 1 times 2 is 2 again. So now, to kind of get this graph so that you can see the difference here, I'm going to graph those 5 points to get myself started. I'm going to graph 0, 2, which is right here. Use a different color. I'm going to graph pi over 2, 0, which is right here, as I mentioned before. The x-intercepts stay the same. If I plug in pi here, I got -2. So it's affecting, as you can see, the highs and the lows, the amplitude. If I plug in 3 pi over 2, I'm back to 0. 2 pi, I'm at 2. Now, 1, 2, 3, 4, 5 points. Those 5 points are enough to come up with a reasonable sketch of what's going on with my curve. Because I know the basic shape, the wave. Now I just have to kind of stretch it out a little bit. Now don't connect the dots like it's a bunch of line segments, because that's not a... Oh, I went a little too far there. For right now, do you see these 5 points and see the curve there? Compare it to the one in pink. This is kind of a purple color. Compare it to the one in pink. Do you see how it's been stretched? How the x-intercepts stay the same, but my highs and my lows have changed? And this would continue. And this way as well. Do my best here to come up with a reasonable sketch. And you can see how it's changed. Notice here the amplitude has changed. Remember we talked about amplitude in the last section for the sine and for the cosine functions. There's this descriptor called amplitude, which talks about the highs and the lows. It kind of gives the range of the values. And in this case, my high is 2, my low is -2. My amplitude would be 2 minus -2 all over 2, or 4 over 2, which is 2. Notice that it is doubled from the regular graph that I had here before, y equals cosine x. It is doubled because the midline here, which is the x-axis, it's 2 this way, it's 2 this way. You can see that you get the amplitude of 2. So it's key here that this number right here is going to tell us something about the amplitude of our graph. Now let's jump back to this one we had before. This was y equals the sine of x, has the same domain and range as the cosine function. But as you can see here, this time I am going to take the sine of x function and I'm going to multiply it by -1/2. Now the negative here is going to reflect it in the x-axis. It's going to make all the positive sine values negative and all the negative ones positive. So I'm going to get to that guy here, but the 1/2 is where it gets a little weird, because the 1/2 is going to cut all these x values down, all these sine of x values down, I should say, by a factor of 1/2. As you can see here, the absolute value of A is 1/2, which is between 0 and 1. It's going to compress my graph. It's going to kind of flatten it out a little bit. I'm still going to have the same exact x-intercept, so I don't have to worry about that. Let me get a different color for this one. I got a pink one here. How about that? So my x-intercepts are going to stay the same. But what's going to change are my highs and my lows. And remember, it's going to be reflected because of the negative. So let's plug in these 5 key values again. Same 5 key values I used before to get my highs and my lows and my x-intercept. So if I plug in 0, the sine of 0 is 0 times -1/2 is still 0. Okay? If I plug in pi over 2, the sine of pi over 2 is 1 times -1/2 is -1/2. If I plug in pi, the sine of pi is 0 times -1/2 is 0. If I plug in 3 pi over 2, the sine of 3 pi over 2 is -1 times -1/2 is +1/2. And if I plug in 2 pi, the sine of 2 pi is 0 times -1/2 is 0. So remember this part here, if you can, well, it's been a while if you watched the other video, but this part here where all the little dots are, that was my original period of the graph of the 2 pi here, the fundamental period of 2 pi. So what I'm doing is the same from 0 to 2 pi, but you're going to see how it's affected. Now I already told you that these haven't changed, and you can see that they haven't changed. Those 3 points. What's changed are my highs and my lows. Pi over 2 gave me -1/2. That'd be about here. And 3 pi over 2 gave me +1/2. You can see, I hope anyway, the reflection in the graph. You can see that it was above, now it's going to be below. I'm going to try to do my best here. I still have that sine wave, but now it's been reflected and it's been compressed. And I'm going to continue with this. Now you can see here this would be at -1/2. And then back to here. This would be at +1/2. Continue the pattern. Thank heavens for these nice periodic functions. And so on. Looks a little bit like a spiral for like a DNA curve or something, like a DNA coil. So anyway, now let's jump over here to the idea of the amplitude. The amplitude here, notice, is my high is +1/2, my low is -1/2, so it's +1/2 minus -1/2 divided by 2. This is 1 divided by 2, or 1/2. Now I want you to notice something here. I want you to notice that my A value was -1/2, my amplitude is 1/2. My A value here was 2, my amplitude was 2. That's going to tell me a lot about the amplitude when I am multiplying the trig function, the sine or the cosine function, by this constant A. Now, that's affecting the highs and the lows. It did not affect the x-intercepts. It did not affect the period. The period is exactly the same as the original. The period for both of these graphs there is 2 pi, the fundamental period. But now if we multiply the x value, not the cosine of x, but the x value. The x value here by some constant which we'll just call b, not equal to 0 or 1, so that it looks like this. We have the sine of bx, or we have the cosine of bx. This is just very general here. It's the graph of the original function with a horizontal stretch or shrink. Now, instead of stretching or shrinking it vertically, we're going to stretch or shrink it horizontally. And it's kind of the opposite here. When the absolute value of a was greater than 1, we had a stretch. Where here, when the absolute value of b is greater than 1, we actually have a shrink. And when the absolute value of b is between 0 and 1, then we have a stretch. And as I have written down there, although it's kind of sloppy, this is going to affect the period. It's going to, kind of like I used to have a slinky when I was a kid, and you could stretch it out and you can kind of push it back in. It affects the period of the wave, of how often that occurs. And in general here, and I'm going to write this down before I actually do some graphs, in general, if you have a graph, notice here I have both factors. This is the one that affects it vertically, this is the one that affects it horizontally, right? And this is for sine and for cosine. Okay, now in this case I have b is greater than 0, because if b was negative, then you'd have a reflection in the y-axis. We're not dealing with that right this second, but as long as b is positive, the amplitude and the period are, amplitude was, as I was mentioning before, is the absolute value of a. Remember, this was a 2, this was a 2. This was negative 1/2, this turned out to be positive 1/2 for the amplitude, the absolute value of that. So the amplitude is going to be the absolute value of a, but the period is affected in this manner. We don't multiply by b, we divide by b. We take the fundamental period of sine or cosine, which is 2 pi, we divide it by that constant. So if b was, let's say, 2, then 2 pi divided by 2 would be pi. We would cut the period in half. And as I mentioned before, and I did one over here, when a is negative, it's reflected in the x. If b is negative, it's reflected in the y. What we need to do is we need to get after some examples here that have both a horizontal and a vertical dilation, stretch or shrink. And we're going to do that here in the next video.